A stack is a way of storing data that can be helpful with things like reversing inputs, managing undo operations, and evaluating expressions. This video is about the data structure itself. I also have videos about how we implement stacks in arrays and linked lists. Now, before we go too far, let's make sure we remember what a data structure is. It's a description of how we can store data and some operations that we can do to that data that gives us some specific functionality. The description of a data structure is implementation independent, but once we've built it, we can reuse that code for many situations. In addition, it gives us a higher level of abstraction that we can use when we're talking about what we need to build. The data structure known as a stack behaves just like a stack of dishes. When you put a new one on the stack, it goes on the top, and when you take one off, you take it from the top. For this reason, it's often called a LIFO data structure, last in, first out. So, a stack has to be able to store a bunch of things, and we have to know where the top of the stack is. Once we have that, our stack has to support three operations. The push operation puts a new element on the top of the stack. The pop operation takes the top thing off the stack and gives it to the caller. And isEmpty returns true only if there is nothing in the stack. In addition, some implementations of stacks include the peek operator, which lets a caller see the thing at the top of the stack without removing it from the stack. As an example of using a stack, let's use one to reverse a series of characters until we enter a percent sign. That sounds hard. Let's start by just saying the user has to enter three things and then we'll output them backwards. Here's my pseudocode. 3 times we get a character from the user and push it onto the stack. And then 3 times we pop the stack and output what we get. Let's run that once to see what happens. The first input the user gives me is a B, and I put it on the stack. The second input the user gives me is an A, and I put it on the stack. The third input the user gives me is an N, and I put it on the stack. Now I pop the stack, which gives me the N, and I print it out. I pop the stack again, which gives me the A, and I print it out. Finally, I pop the stack one last time. That gives me a B, and I print it out. So the user gave me BAN, and I printed out NAB. Successfully reversed. Our original challenge was to take the input from a user until we saw a percent sign, and then output it in reverse. That's going to require 2 loops. Just like our simpler implementation required 2 sets of things that we did 3 times each. The first loop is going to get input from the user until we see a percent sign, and the second is going to output what's on the stack until the stack is empty. Count controlled or sentinel controlled? Sentinel controlled, because we don't know how much input the user is going to give us before we see a percent sign. Here's my pseudocode. 1 loop getting input and pushing it onto the stack. And that loop keeps going until it sees a percent sign. Notice that the percent sign will not get pushed onto the stack. The second loop runs while there's something on the stack, and it just pops the top off and prints it. If you are unsure why that solves the problem, be the machine. Run it yourself with some sample input and see what it does. One of the tricks of being a good software engineer is to be able to detect patterns in what we want to do. Think about the undo command many pieces of software have. Essentially, undo is last in, first out. The thing we want to undo is the most recent thing that we did. And if we undo more than once, we should walk back in time through the options that we did. LIFO tells me that we need a stack. If, for every operation, you push onto the stack either a description of the operation or the state of the system before the operation was done, then undo is just pop the top operation off the stack and put things back the way they were. That's the basics of the stack data structure, but there are 2 things that could go wrong if someone misuses our stack. They could try to pop a stack that doesn't have anything in it, or they could try to push something onto a stack that is full. Yes, some stacks have limited space. How we handle these issues is pretty language dependent. If our language supports throwing exceptions, that's an obvious good strategy for handling these things. If not, then we need to return something to tell the caller about the problem. For popping a stack that is empty, we can return a flag value denoting the error. But we need to pick a flag value that could never be a valid stack entry so that the caller can detect that the problem has occurred. What that value is depends on the specific problem that we're solving. For pushing onto a full stack, we can make push return a Boolean. True means everything went okay, and false means that we didn't complete the push. The most common ways to store a stack are in an array or a linked list. I have other videos that show exactly how we do those kinds of implementations.